and especially of the CERA team there. And so I will speak about CS today and about AI, and this is all part of a bigger project that is funded by Schmidt Science, our foundation from the US. And the results I will show are also a bit connected to a smaller LeFi-MENU project and our PNTS project, all about generative AI. And yeah, as the title says, I will speak about two revolutions today, not only one but two. And if we look at the first revolution, you might all be aware of this first revolution because the first revolution is connected to machine learning, AI, and weather forecasting. And so, for example, the Wired magazine has titled the last year that AI can now do hurricane prediction. And then there are now many neural network models, AI-driven models to do weather prediction. And one of the more well-known is the so-called GraphCast model developed by Google DeepMind. And this work was basically more or less the first work where they show quite reliably that they are better doing than the geophysical weather forecasting models developed by the ECMWF and by NOAA and so on. And so actually the ECMWF was also forced to publish their own AI-driven models. So they are now doing also a lot of AI-driven weather prediction modeling. And they introduced last year the so-called AIFS, so the AI version of the integrated forecasting system. And all these models have in common that they always show that if you look at the synoptic scale, if you look at the most important scales for weather forecasting, at least for medium range weather forecasting, we see curves like this. So here on the y-axis we have the error, on the x-axis we have the lead time of the model. And so this is, for example, the geopotential height in 500 hectopascal, one of the most important variables for synoptic scale and weather forecasting. And here the red curve is the curve from the IFS model, so the operational weather forecasting model of the IFS. And the dark red curve is the AIFS, and we can actually see that the AIFS has actually a smaller error than the IFS, than the conventional geophysical model. And so this is what I call here, and many people call the data-driven revolution of numerical weather prediction. And the main idea was now to use this revolution also for CS modeling, to build a next generation CS model. And as I said, this is all part of a bigger project. So this is all part of the so-called scale-aware CS project, where we try to build a next generation CS model, which is called NextSim, and with a quite advanced mathematical framework. And this model is built around the idea of the most important processes in CS. So first of all, CS is multifractal and anisotropic. So meaning there's no specific length scale in CS. So meaning the same processes are working at length scales of 100 kilometers, but also at 10 kilometers. And then also we have anisotropy. So this means if we have, for example, a crack in sea ice, this crack will develop along a favorite direction, so along more or less the same direction. And then also a very crucial part in sea ice is that we have rapid changes. So meaning sea ice is by definition only by definition only on ocean. And so we have a very rapid transition from open ocean water to sea ice. And so meaning that this is the so-called marginal ice zone. And we have a very quick transition within, let's say, 10 kilometers or something like this, from really open water to really fixed sea ice. And so this means these processes are kind of hard, are complex. And so we have really complex processes to represent. And because of this, We have also many interfaces with other components of the Earth system. So we have an interface with the ocean, we have an interface with the land, and for sure also with the atmosphere. And then because of the complexity and because of these many interfaces, we need quite advanced modeling techniques. So for example, we are trying to build the next generation of this NextSim model with a so-called discontinuous Galerkin parameterization, which is our very advanced finite element discretization of the system. And so this means CIS modeling is very difficult. We need really advanced modeling techniques. And my main hypothesis here will be that deep learning can actually represent these processes. That deep learning is really now there to basically emulate what the model is doing, to really represent what is happening in the CIS. To prove this, I will do so-called surrogate modeling. So which means we take a neural network, and our goal is basically to use the neural network to replace the CS model in itself. So in some sense, to do emulation of the CS model here. The nice thing about this is if this is working, we first would have a faster version of the model. For sure, we might have an approximation error, but nevertheless, we have a much faster version of the geophysical model. Then, if we do this, we can actually gain insights about the errors of the model and how we can correct these models. And then if we have a data-driven model, we can actually combine this model with data assimilation to then further refine the model with observations and to go beyond what the geophysical model is saying. And so meaning we have the possibility then to possibly exceed the performance of the geophysical model. To do this, the first thing we need is a lot of data for sure. So we need data, we need a lot of data. And here I will speak about data from a simulation with a state-of-the-art CS model. So with the old version of NextSim, which is called the Lagrangian version of NextSim, so because it is based on a Lagrangian grid. And so actually for this simulation, NextSim was coupled to the ocean component of the NEMO modeling framework, and we have more than 20 years of simulation data from this. And in the beginning now, I will just concentrate on a region here north of Svalbard, because first of all, I want to give a proof of concept, and this is much cheaper to give this proof of concept for this region. And also, this region can be seen as, in some sense, representative of the processes in the Arctic, because here in the north, basically, we have already fixed sea ice. We have also cases of the marginal ice zone, and so on. And so it can be seen as in some sense, as a small representation of the processes that are needed for the Arctic. But later, I will then also speak about Arctic-wide results. So we have our data. We have fixed that we want to predict the CS for the 64 × 64 grid points. Now we have to define our task. And the task is here that we have given some initial conditions of our CS. So here I take basically all the predictive variables of the CS model, the CS thickness, the CS concentration, the CS standard, and the two velocity components of the CS. So basically all the variables that describes the state of the CS at the current time. I have to say here, the damage variable is a special kind of variable which comes with the subgrid scale parameterization introduced in NextSim, because this subgrid scale parameterization tries to more or less precisely model how cracks develop from small scales to larger scales, and so our so-called damage variable was introduced, which parameterizes the fragmentation at the subgrid scale. And our goal is then to put this into a neural network, into a surrogate model, and then to predict exactly the 5 variables again 12 hours later. For sure, CS is driven by forcings from the ocean and the atmosphere. And here I will just concentrate on forcings from the atmosphere. We can talk later about forcings from the ocean. And here I will use forcings from Error 5 because the original simulations are run with Error 5 as atmospheric forcings. And I will just concentrate on 4 different variables from Error 5, the 2 meter temperature, the 2 meter specific humidity, and the 10-meter wind velocities, because I want to stay compatible with CMAP6 like forcings, and in CMAP6 we have these variables on our at a 6-hourly scale, and so if I would train this now for the 12-hour scale, I could still use this with CMAP6 like forcings. Then we have to define our data set in some sense. So I use the first 20 years of data for the training, for the optimization of the neural network. An important part is here that I use data augmentation. So I randomly flip and rotate the data. This is needed to basically impose a physical prior into our neural network because the physics that we want to learn, so Navier-Stokes, for example, are rotational invariant and flipping invariant, and so we want to impose this into our neural network. Then I use 2015 for the validation to select the best model, and then I will show results for the. So based on the validation data set, I basically decided to use a UNet, so a convolutional neural network with a vision transformer in the bottleneck, which is also called then UViT architecture. And first I will concentrate on a deterministic model, and so the objective is to minimize the mean squared error of the forecast. And then in the following I will show results over 3 years. And so I have data every 6 hours, and so this means I initialize a forecast every 6 hours and then go up to 15 hours in advance. So meaning the model is trained for 12 hours in advance, and then I can use the prediction after 12 hours as the next initial conditions, then go to 24 hours and further and further and further, and I will do this up to 15 days or even up to 50 days. When we first concentrate on the forecast error, so I will show always a figure like this. So here on the x-axis we have the lead time in days, as I said, up to 50 days. And here I show the normalized root mean squared error. This is the root mean squared error averaged across all 64 times 64 grid points and across all 5 model variables. And I normalized the model variables by the climatology. So this means that I basically got the dimensionality out of these variables. And then the truth is here no observation or no grown truth in some sense, but the NextSim simulations, because the goal is here to really emulate what NextSim is doing. The first thing we need are for sure baseline models. And so the first baseline model is here, as the so-called persistence forecast, where we take the initial conditions and then continuously predict the initial conditions throughout our forecast lead time. And this is actually for sea ice modeling already a quite good baseline method. And then on top of this, I have here a sample dynamical model, which is based on the atmospheric forcing velocities, and based on these forcing velocities, we can then estimate the sea ice velocities, and then we can advect the tracer variables of the sea ice with these instantaneously estimated velocities, which is a so-called free drift model, and which can be seen as a very, very simplified dynamic model. And if we now plot in what our deterministic model says, then we can already see the deterministic model improves both baselines, and actually this holds across all model variables, across all lead times. So I've shown here just an aggregated error statistic, but I've looked into all 5 variables, and for all 5 variables, the deterministic model is here, if we compare these 3, the best model. And so this means that the deterministic model seems to work. If we now concentrate on a single simulation, so here I show now snapshots from the sea ice thickness, so from a single variable, and the first row here is our truth, is what NextSim simulates after 12 hours, after 7 days, and after 50 days. And if we now plot in what the deterministic model says, then we can see that here in the beginning, the deterministic model seems rather fine, seems to do a good job. However, after 7 days, we can already see a problem with the deterministic model because we can see that the large scales still match quite well. However, the deterministic model really smooths out the forecast. And so if we analyze the energy spectrum, so this is the energy spectrum of the field, averaged across the testing data set for a lead time of 15 days. And here we have the energy that is contained in the CS thickness fields. And here on the left we have the large scales, on the right we have the small scales. And so we can see that the deterministic model is actually losing information at the small scales. And this actually then leads to these smoothing effects. And this comes out of the fact that we have trained the model with a mean squared error loss. And the mean squared error loss basically predicts the mean of a Gaussian distribution. And so this then imposes so-called double penalty effect, or tries to reduce so-called double penalty effects. Double penalty effect means that if we have, for example, a crack and sea ice, and the crack is here on the right side, but we predict the crack on the left side, then we do actually the same error twice because we make an error here on the right side and also an error on the left side, and so this means we make this error twice. And the mean squared error basically tries then to take the average because in the mean squared error sense it is better to basically predict the average instead of doing this error. And then last but not least, we can see another issue with the deterministic model, because we have trained the deterministic model for 12 hour lead time, so here, and after 50 days, so after we have iterated the model 100 times, we can actually already see here strange waves, strange strains, and actually this indicates instabilities in the forecast. And so this means the deterministic model smooths out the fields, shows really instabilities, and this brings me then already to the end of the first part. That first of all, the deterministic model is very, very fast because we take the fields now, just predict the fields 12 hours later, and do it over and over again, and so we can actually be around 1,000 times to 10,000 times faster than the geophysical model itself. But it smooths out the forecast fields and it results into instabilities. Now let's come to the second revolution. Or do you have I think I can build in some short questions if there are any, or we can discuss later. But
what is energy mass?
So no, this means so this is the Fourier spectrum of the fields here, averaged across the whole testing data set, and the Fourier spectrum tells you something about how much energy is within these fields. And so meaning this is what I've shown here on the y-axis, and so basically, yeah, it's then yeah.
Sorry.
Yeah.
I didn't understand very well the deterministic model and the dynamical one. I suppose that the deterministic model is that you use initial condition forcing out and a neural network to predict your size.
Yeah, the fields, yeah.
And so the simple dynamic model, what is
for this, so you can do a scale analysis of the momentum equation for CS, and you will actually see that CS has the two important parts for CS for the momentum equation are actually the drag from the atmosphere and the drag from water. Since we don't use any ocean forcing here, I just concentrate on the drag from the atmosphere, and based on this, we have an analytical solution for given the atmospheric forcings, we can estimate the instantaneous CS forcing or the instantaneous CS velocities, and then we can use the CS velocities in Lagrangian modeling framework where we basically advect the tracer variable, so C as thickness, concentration, and damage, with the instantaneously estimated fields based on the forcings, and then yeah, we have basically we completely neglect the thermodynamics and also important parts of the dynamics, but we just have an advection model. And so because it is still based on the momentum equation, it can be seen as some sort of simple dynamic model. If there are any questions in Zoom, then yeah, feel free to ask them. Now let's come to the second revolution. And the second revolution starts with text. So here I show a small text, a high contrast portrait of a very happy fuzzy panda dressed as a chef in a high-end kitchen making dough. There's a painting of flowers on the wall behind. And nowadays, neural networks can generate images that look very realistic. So in fact, it is a bit hilarious because a panda is making dough. So it is unrealistic. Nevertheless, the picture in itself it looks very realistic. And actually, this picture is already 2 years old. So nowadays the generative AI models are much further. And the second example is then again text, but now we have a drone view of waves crashing against the rugged cliffs along Big Sur's Garry Point Beach. The crashing blue waters create white-tipped waves while the golden light of the setting sun illuminates the rocky shore, and so on and so on. And since the beginning of this year, AI can actually generate very, very realistic looking videos. Just out of this text. Why is it so slow? It doesn't matter. And so, as I said, AI is now also there for generating videos. And this is actually also this is from the beginning of this year, and the AI actually developed even further throughout this. And if we think about the geophysical forecasting problem, then actually geophysical forecasting can be seen as a video because we have our fields that we then also move forward in time or backward in time, and so this is exactly what a video is doing. And so this is what I call here the revolution of generative computer vision, and my take on this is that this will be also a revolution for geophysical modeling. So let's come to the main idea why we got this revolution quite recently. The first thing is, so I've shown you until now a deterministic model. So if we imagine our forecasting problem as we have some starting point, some initial conditions, we have a target point. What we do with the deterministic model is we make an explicit distributional assumption. So in this case, a Gaussian assumption. We predict the mean of this Gaussian, and this mean is then the prediction of our deterministic model. And so actually the mean squared error can be reduced to this assumption. And if we now want to train when we train a neural network as a generative model, we do something different because we simply generate states. So meaning we don't do an explicit distributional
Shawnee, we don't have the sound anymore. You are muted if the sound comes from your computer.
But if I use my computer sound, it will produce.
Yeah, we should be good.
Is it fine now?
Yep.
Okay, perfect. So I will just make everything worse.
So we lost the sound when you were showing the first target, difference between deterministic and
Ah, yeah, okay.
generative stuff.
Yeah.
Yeah. Thanks.
You're welcome. So in a deterministic model, we make an explicit distribution assumption, and in generative modeling, we just learn how to sample states. And the nice thing about this is then we can then sample many states from one set of initial conditions and forcings. And to train such a model, this is a so-called denoising diffusion model. And to train such a model, we take our data that we want to predict. That is our goal to predict. And then we add a bit of noise. And this bit of noise replaces some information in the field by noise. And instead of adding noise just only once, we add noise many times until we have completely replaced all the information in our field by noise. And so this means here in the end, actually our field is completely decorrelated because it is drawn from a normal distribution. And then we train our neural network to do the reverse step. So we train our neural network to denoise a tiny bit, but instead of trying to denoise all at once, we just try to denoise a tiny bit. And for sure, we want now to train the model to do a conditional forecast. So meaning if we would do it like this, the neural network wouldn't know about the initial conditions and the forcings. And so what we can do is actually we can take our initial conditions, we can take our forcings, and simply concatenate them together, or give the neural network the noise field as input and the initial conditions and the forcings as input. And then the task of the neural network is, given this information, to predict the field, the previous field. And instead of training a neural network for each noise level, we amortize the neural network. So which means we train the same neural network over all noise steps by additionally giving as information to the neural network at which noise level it is. And then the same neural network can be applied for any given noise amplitude, for any given noise level. And at all steps, we condition the neural network on the initial conditions and the forcings. In this way, actually, the neural network, so the initial conditions and the forcings help the neural network to learn to denoise. And actually, then if we then train this neural network, the result of this neural network will then result into a sample from the conditional probability distribution, or the probability distribution condition on the initial conditions and the forcings. And the nice thing about this is because we know the way of perfectly analytically how we get from our target data to pure noise, so we can sample any noise level in between. And so we can actually train the neural network by a supervised loss function as for the deterministic model. So it can be seen a bit similar to the deterministic model, but now we have noise data, and we want to and we basically train the neural network to denoise a tiny bit. The question is now, when we now want to forecast, because we have our conditioning information, so we have our initial conditions, we have our forcings, and now we want to generate a forecast. So remember this picture here in the lower left, that we want to generate samples from our probability distribution. What we can do is we can actually sample from a Gaussian distribution some random fields, and then we apply our neural network conditioned on the initial conditions and the forcings, and this will denoise the field a tiny bit. And instead of doing this just only once, we can do this many times until we have our clean field. And the nice thing about this is that there are actually many different formulations, but my favorite formulation is that this is basically an ordinary differential equation. And so this is basically a deterministic forward step. And the nice thing about this is then that we can change the initial field here, and we get a different answer here. So this means this whole model will be then stochastic, despite the fact that we just give one set of initial conditions and forcings. Now let's remember this figure. So meaning we train our diffusion model to do a 12-hour forecast, and then as for the deterministic model, we can then cycle the forecast autoregressively. So we can take the output after 12 hours again as input for the next time step, go to 24 hours, to 48 hours, and so on and so on. And the nice thing is, since this is a stochastic model, we can start with one set of initial conditions at a lead time of 0 hours, and then generate an ensemble of predictions. And if we do so, we can actually see, so I've shown here two different lines. The first red line, the dashed line, is the forecast of a single realization of the diffusion model. So basically, if you want to say so, the ensemble mean of a single run. And so we can see that actually especially initially, it is worse than the deterministic model. But this is actually expected because of the previously mentioned double penalty effects, because the generative model doesn't care about these double penalty effects, whereas the deterministic model cares about it. And so if we look at the root mean squared error, the single realization is worse. However, if we take an ensemble of 60 ensemble members and use the ensemble mean as prediction, then we can see that the ensemble mean is actually always better than the deterministic model. And the reason is actually that the deterministic model basically models the ensemble mean, or is trained to represent the ensemble mean after 12 hours. But if we cycle the deterministic model, it will diverge from the ensemble mean, because it is in some sense the ensemble mean of the ensemble mean and so on, which is no longer the ensemble mean. And so a true ensemble mean will be then better than the deterministic model, and which is pretty great because we haven't explicitly trained the diffusion model to minimize the mean squared error of our forecast, but of a surrogate in some sense. And so nevertheless, the diffusion model improves the forecast by around 12%.
Just one quick question.
Yeah.
When the averaging of ensembles is a simple averaging, or or the weight is also a limit factor?
No, it is really just doing 16 ensemble members and then taking the average as prediction. So it is our clean average.
You average for each grid point.
Exactly. I average for each grid point independently. So this means that no, we don't see this later, but the ensemble mean is then no longer a physical realization in some sense. It's a proper ensemble mean, as you would expect from. So it has exactly the same properties as an ensemble mean from a geophysical model. However, if we now look again into our snapshots from a single realization. So I will now show for the generative model a snapshot from a single realization. So not the ensemble mean, but a single realization. And if we now plot in what the generative model says for exactly the same situation, we can actually see. So we can see by inspection that the generative model keeps the sharpness throughout all the forecasts. So the energy spectrum is almost perfectly matched between Nextsim and the diffusion model. And we can also see that for sure it might look different after 50 days. But nevertheless, we can actually see that these artificial strains are no longer there. We can even detect small strains here. And so when I would now give you this field and this field, I guess you couldn't say which one is the true field and which one is the generated field. And now let's let's concentrate a bit further into what happens after 50 days. So into what happens after we iterated our neural network 100 times. In CIS modeling, we know certain connections, certain links between specific variables. So here I show the CS concentration, and so darker colors means less CS concentration, so less CS in a grid point, and this is the deformation. So the deformation is diagnostic variable estimated out of the predictive CS velocities, and so in our true data we can really see the physical links that we have less CIs, and this less CIs is then linked to a strong deformation of the CIs, so to stress within the CIs, and then actually this stress can then change the thickness of the CIs. So this is the change of the CIs thickness within 12 hours. And so, for example, for this strain here, we see here a blue change in the CIs thickness. So this means it is a thinning of the CIs, and so the deformation is then very, very likely a divergence of CIs. So meaning the CIs diverges there, which then leads to a thinning of the CIs. If we now look what the deterministic model says, then yes, we still can see relations between these variables, but because of the smoothing and because of these artificial strains that we can actually also see quite heavily here, it no longer looks really physical. However, if we now look what the generative model says, we still see the links between the variables, and we see that it might look a bit different because the trajectories might have diverged, but nevertheless it looks very, very realistic still. And if we analyze, so which means in fact that the generative model leads to physically consistent forecasts. So we still have the correlations between variables, between grid points, and we can really say it looks very, very consistent. And actually one of the most important variables in CIS is the deformation, because if we have strong deformations, we can expect heavy changes of the CIs and strong CIS dynamics. And here I show now the histogram of deformation values in a log-log scale, and because only the strongest deformation values are important, and we can actually see that for the shear deformation and also for the divergent and convergent deformation, so for the total deformation, the generative model, the diffusion model, basically matches the histogram of Nexstim, whereas we clearly underestimate the low values of deformation. And if we look a bit closer into the deformation values, we can see that this might be a bit noisier, which then basically explains why we have shifted mass here in the histogram from there to there. And so meaning because we basically have a dynamic system, as I said, and we have to discretize this dynamic system in the diffusion model and integrate it and so on. So we have an accumulation of small errors, and this likely leads to these noisier fields. But nevertheless, so I've not shown it here, but one can also analyze the structure function of CS. So how the deformation changes when we cross-grain the data and so on, which is an indicator for the multifractality of CIs, and we can actually see that the diffusion model does a pretty good job. And so this means that the diffusion model has seemingly, in some sense, some sort of physical laws that are similar to those from Nexstim. But I wrote here physical in parentheses because it's for sure the diffusion model is not physical. And then for the regional model, at last, this is the thing that amazed me the most, is to test a CS dynamics model, there is some sort of benchmark case where we have an atmospheric cyclone shown here on the top right, which then moves from the lower left of the domain to the upper right of the domain. And here I show the CS thickness, the CS concentration, then the speed of the CIs, and the divergent component of the CS deformation, the shear deformation, and the total deformation. And if we now let the cycle moving forward in time, then we can actually see a behavior of what we would expect from a geophysical CS model. So if we would let Nexum running at this resolution, we would get very, very similar results for the deformation. And then we can even see when we jump to the end that we have here a thicker CS thickness, or the CS is thicker here, and this is actually the path of the cyclone, and this means that the CS thickness really reacts to the convergence of CS and shows this path. And so this means actually that this model almost perfectly, or not perfectly, but it works pretty well for a very idealized case. And since the model was trained on realistic data, on reforecast data, which were run with RF5 forcings, and here we have really idealized forcings, this really suggests that the diffusion model generalizes well to unseen settings, and might have some sort of understanding of the physics, whatever it means in terms of neural network, but it shows a good behavior, as we would expect from a geophysical model. I could do a small break again here. There won't be so many slides left, but if there are some pressing questions, feel free to ask them. Otherwise, I would simply continue. Because as I said, so the nice thing about the deterministic model is it takes the initial conditions, we apply the neural network once, it produces an output. So meaning it is really fast. However, for a diffusion model, we have to apply our neural network, let's say 50 times in total. So which means the neural network is 50 times, well, the forecast is 50 times more expensive than a deterministic forecast, which is still cheaper than a geophysical than a forecast with a geophysical model, but nevertheless, it is much more expensive. So for example, for the 3 years of testing data, for the 15-day lead time and so on, I needed around 1 day to basically evaluate one run with the diffusion model. And so the scaling to Arctic-wide global settings is kind of difficult. And the first thing I investigated for this, or we investigated for this, is to use so-called latent diffusion, which is actually used quite heavily for image generation, because for images you can imagine you have exactly the same problem. You want to generate a high resolution image, and you might have to wait half a minute to get the image, but you want to get the image after 1 second, let's say. And so this is a solution that is quite heavily used for that. And the main idea is that we take our data, so here now Arctic-wide data, and we basically pre-train an autoencoder which compresses our data. So we train 2 additional neural networks, one encoder and one decoder, to compress our data into a latent space, and then we apply the diffusion model in this latent space. And since we have a compressed space here, it is much cheaper to apply the neural network in there. And one additional advantage of this is, so it is much faster. And one additional advantage is that this diffusion process is really linked to the Gaussian distribution. So meaning, if we want to change the distribution, if you want to incorporate prior physical knowledge into our diffusion process, it might be kind of difficult. But this is the nice thing about this autoencoder architecture, because in an autoencoder we can basically do whatever we want, and so we can incorporate prior physical knowledge. And for example, here I basically made use of the prior physical knowledge that we know that the CS thickness cannot be negative; it can be 0, exactly 0, or larger than 0. And so I use here a so-called censored Gaussian distribution, which is similar to a truncated Gaussian distribution, but instead of truncating so that no value is possible for 0, it basically sets all the values that are smaller than 0 or exactly 0 to 0, and so it can be seen as a distributional version of the ReLU activation function, for example.
So the latent space, sorry.
Yeah.
It means decomposition of the larger space into several sub-regions.
No. Here I basically simply compress the data. So meaning you could in fact imagine this a bit like a PCA UF. Because UF is a linearized version of this basically, but instead of doing a linear transformation, you do a nonlinear transformation from data space into a compressed space, and then you apply in this compressed space our diffusion. And so yeah, we can also incorporate prior physical knowledge, and so this means it seems very, very nice. In fact, we can be up to 25 times faster than with our diffusion model in original space, and then we can incorporate prior physical knowledge. However, there's also a pretty big caveat, which is especially difficult for geophysical forecasting, because here I show now 2 snapshots of the thickness, concentration, speed, and deformation. The first row is with a diffusion model in data space. The second row is a diffusion model in latent space. And what we can actually see is, if we concentrate here, for example, on the deformation, we can nicely see cracks in here. However, if we look now closely here at the latent diffusion model, we can actually see the latent diffusion model smooths the fields out. And so we are back to the smoothing issue, which means, in fact, if we look again at the energy spectrum, we can actually see that we lose again information at the small scale, as we do with deterministic modeling. And so the light blue line is the autoencoder without any diffusion model. And so we can really see that this comes out of the autoencoder. So meaning, even if we wouldn't use the diffusion model and just the autoencoder to compress and then to decompress again, we have this loss of small scale information. And for image generation, they use certain tricks, for example, adding an adversarial loss and so on. However, for geophysical modeling, this is not really an option, because this then results into a much more difficult training, into under-dispersion, heavy under-dispersion. And so this means that actually for geophysical modeling, despite the fact that it seems very nice, we get a faster version of the model, we can incorporate prior physical knowledge, this doesn't seem like a solution. And so I was working the last 3-4 months on another solution, which is called patching, or which can be also called classical domain decomposition. So as you would decompose the fields in classical geophysical modeling. So the general idea is that we basically use a regional model, and a regional model that is applied on all patches, or on all subdomains from the full CI sphere at the same time. And the thing is that instead of just concentrating on our subdomain, we have also a boundary condition, a boundary grid points in the boundary. So we have basically overlaps between the patches, and so since one idea would be to decompose the field before applying anything and then composing it back to again at the end after generating the data. However, the better solution is to decompose before the neural network is applied and to compose it again back together after applying the neural network. And so since we apply the neural network, let's say 50 times, we basically smooth out boundary effects between the patches, and this can be really seen like the neural network represents the time derivative, and then to basically discretize the time derivative in classical geophysical modeling, we would also do the domain decomposition and then communication between the subdomains after each integration step. And so this basically reflects exactly the same strategy. And so with that, I basically achieved that the neural network is then trained as a regional model. So I also use this patching approach during the training. So meaning I randomly sample a patch from the full field, and then train the neural network, on such patches. And so this means I never have to load the full field into the GPU memory at the same time. So I can train it with much bigger batch sizes, for example. And then also, if I then apply the neural network, I then achieve our 12-hour prediction on a single GPU in under 1 second. And actually, the neural network can be, as I said, then trained on a single GPU. It can be applied on a single GPU, which is a difference, for example, to the global weather forecasting model of Google, because Google uses, I don't know how many TPUs at the same time to train the diffusion model. And so with such a strategy, we can actually do it much more efficient. And then the nice thing is I now use a transformer only architecture, which actually scales quadratically with the number of bit points. And the nice thing about the subdomain domain decomposition is that within a subdomain, the neural network still scales quadratically with the number of grid points in a subdomain. However, it scales linearly with the number of global grid points. And in theory, it also scales linearly with the number of GPUs. So if we have more GPUs, we would expect some sort of more or less linearly scaling of the forecasting. And if we now look into the forecast scores for the Arctic-wide settings, then here I show the persistence forecast, then a forecast from a deterministic-like model. So basically a deterministic model. And if we now plot in what the diffusion model says, so this is just for the validation data set, so just for 1 year. So this is why the curves are a bit wiggly. But nevertheless, we can already see that we get basically exactly the same results as for our regional setup, which means the results seem to translate to the Arctic-wide setup. And then a very nice thing about the speed is that we can actually do very long forecasts. So I just wanted to ask if you have questions. But so I think I have to. Do you still hear me? No, I don't think so. Yes.
Okay.
Yes. Okay, perfect. So what I did then, I just used the neural network trained for a 12-hour forecast and let it run for 3 years. And since the neural network is quite speedy, I can run the 3-year long forecast in around 30 minutes. Whereas actually with the original Nexter model at this resolution, they need for 1 year around 1 day. So meaning this is much faster. And so if we look of how the fields look after 3 years, then for sure, again, after 3 years, we cannot expect that the fields look exactly the same because we make a forecast for 3 years, the trajectories diverge and so on and so on. But nevertheless, the fields look still very realistic, and it looks reasonable. And yeah, and I mean this is really after 26,000 hours of forecast. And then we can also evaluate how the CS extent looks like after these 3 years or within these 3 years. And we can actually see that the CS extent simulated by the diffusion model looks very similar to the one from NextSim, except the refreezing period. But I'm working on this right now. So which basically suggests that the model is really stable. It It works for the 3 years out of the box, and gives reasonable results. I started this talk by giving a hypothesis that deep learning can now represent the needed physical processes, and what I've presented, it seems like it is the case. So this was basically the first generative diffusion model that is really tailored to the CS physics. And so this diffusion model then basically unlocks that we get an improved data-driven modeling. And so I then also show in the paper that this can be used to do model error corrections of let's say a geophysical model or a deterministic neural network. And then it basically exhibits more or less the same physical laws as Nexstim, as the geophysical model that we try to emulate, and it maintains the sharpness throughout all lead times. And then with this patching approach, with this classical domain decomposition approach, it scales also to Arctic-wide models, and this could then enable actually a very efficient training of such a model and a very efficient application of such models. Or what we can even do is we could generate data at a coarse level and then use a small refine at a given patch and so on. So there are many combinations then possible, and so this might then enable us to get an efficient generative CS model that is also actually scale aware, which then fits into the scale aware CS project. So for the research setup, I have a paper in James. The paper for the latent diffusion model, I presented it at a workshop at the ICML this year. So at the International Conference on Machine Learning, and I'm currently working on the paper with the patching approach. And this is it. I thank you for your attention, and if you have questions, feel free to ask them. Yeah.
Can you explain again how do you do when you have the patchings? How do you reassemble, or how do you imagine to do the whole?
Yeah. So what I do is basically I have the patches. So let's say the core patch is again 64 times 64 grid points.
For each patch, you have the same neural network.
Yeah, exactly. I use exactly the same neural network for each patch, and the neural network actually is because I use a transformer neural network. So the neural network doesn't know about the absolute position, but only the relative position between pixels. And so when I reassemble the field after applying the neural network for one step, I then just take the core patch, the 64 times 64 grid points, and I disregard the boundary regions.
So yeah, my question was that you don't need actually to do the first patch on the top left corner, then you move the patch. You can do the patch like once.
Exactly. So I can basically move the patch. So meaning I have, when my patch size is 64 times 64, and I have 512 times 512 pixels in total. So this means I have in total 64 patches, and I can move the patch size to the batch size actually. So meaning I can process all patches in parallel.
So you don't need to do first the top
Exactly. And so this means I can then also share basically the patches across GPUs if I want to go towards really high resolutions and I have multiple GPUs and then do a parallel processing quite natively.
This is something that I didn't understand. So you have several patches, and each patch can use the model, and we can run the model training in parallel at the same time from different GPUs. But that means the neural network behind each patch will be somehow different, with different parameters.
No. Actually, so I I train the neural network by simply randomly slicing patches out of my original data with 64 times 64 grid points, and I train then the neural network with a quite large batch size simply. So with many samples at the same time, but then just with random patches. And so I train one neural network for basically regional CS modeling. And then if I want to apply the neural network, I use this patching approach during inference. Because it is basically trained as a regional model, and this is basically a small region, and it is trained to do a regional model for one single step. Yeah.
So just with one patch for training, and then you apply the model to the whole region.
Exactly, but meaning instead of just concentrating on to train the model on a small region as I did before, I just randomly pick a patch across the full Arctic. So meaning that it is trained across the Arctic.
And so while training, would you batch, will the sample in your batch be a different location for the same time? Or
No.
would it, so we do for different times along the batch axis?
Yeah, so what I basically do, I load a single sample, I patch the sample, and then I basically disregard all the things that I did use.
And is the spatial propping the same along all the batch axis?
Yeah.
Does that, is it important? Like, wouldn't it be better if it was different? I don't know.
So actually, so I was talking in the end about the scalar aware CS model, and so what I plan also to do is actually to also coarse grain the data, and then to patch this coarse grain data. So meaning training the same model on coarse grain data and on original data, and so meaning always use the same patch size. Because this enforces basically the uniformity of my batches, but what happens within a single sample is in some sense independent. So I can use their really coarse grain data. I could possibly use even data from a different model, and then train the neural network across different resolutions